Welcome students to video number 2 in our series of lectures about chemistry. So in the first lecture we talked about matter and energy, atoms and elements, and then molecules, compounds, and mixtures. This lecture is going to focus solely on section 2.4 and chemical bonds, which is unarguably one of the most difficult concepts that students have in this chapter. First, let's start off with just what a chemical bond is. Essentially, it's an energy relationship. It's electrons of nearby atoms reacting with one another. And let's go back to our Bohr model again, where we have our central nucleus, and then we have all of these kind of clouds of electrons around the central nucleus. Well, each of these electrons around the nucleus occupy a certain energy level, a certain distance away from the nucleus of the atom. And then we call that an electron shell. And we have up to 7 electron shells around the elements on our periodic table, of which several were just added, which is kind of cool. So the outermost shell of the electrons is called the valence shell. These are the ones that are furthest away from the nucleus, and so these are the electrons that have the most energy, the most potential energy, and are the ones that are reactive in terms of forming bonds between different atoms. So all of the atoms that form bonds are all the electrons that form chemical bonds are the electrons in the valence shell. And chemical bonds follow a principle called the octet rule, which essentially states that with the exception of the first shell of electrons, and really this mostly affects really small molecules, or really small atoms like hydrogen, all of the other atoms, they want to interact with other atoms so that their valence shell is full, and it's considered full when it has 8 electrons in the valence shell. And so that's why it's the octet rule, or the rule of 8s. So chemically inert elements, things like the noble gases like helium, neon, argon, we consider these unreactive elements, inert elements. They're not really going to react with a lot of other elements because their valence electrons their valence shell is already full. Here's helium. It only has 1 electron shell. That first electron shell is full at 2 electrons. So it's done. It's stable. It's not going to react with a lot of other things. Neon here, it has 8 electrons in its outer shell. And so it has a full valence shell, and so it also is stable, inert, and unreactive, and not going to make a lot of molecules and compounds with other atoms and other elements. Conversely, the really reactive elements are those who don't have a full valence shell, and so they're going to interact with other elements to gain, perhaps, lose, perhaps, or share electrons with another atom in order to make themselves stable. Hydrogen, carbon, sodium, oxygen, all the examples that you see here, these are very, very reactive elements that are going to interact with a lot of other elements to form chemical bonds. Bonds between the valence shells and the electrons of the valence shells. So we have 3 primary types of chemical bonds. We have ionic bonds, covalent bonds, and hydrogen bonds. We're going to describe what each of them are, look at some examples, and also talk about them in terms of stability. Let's start with the ionic bonds. when an atom either gains an extra electron or 2 or 3, or an atom loses several electrons, it now becomes an ion. It becomes charged. And so in ionic bonds, one atom will give up a electron or more and becomes a cation, because it's losing electrons, and it becomes positively charged, and one atom will become an anion. It'll have a negative charge because it will gain those electrons that it got from the other atom that it interacted with. And so it's a transfer of electrons. One element, one atom, takes the electrons from another atom, another element. And it's that attraction of a positively charged anion and a negatively charged, a positively charged cation and a negatively charged anion that forms that ionic bond. Let's look at an example. So here you go. Sodium chloride, salt. It's a very, very common example of a ionic bond. Here you can see sodium, it only has one electron in its valence shell. Conversely, chlorine has 7 electrons in its valence shell. And so sodium gives up its 1 electron to chlorine, and now chlorine has a full valence shell and is stable and becomes a negatively charged anion. And sodium has lost that outer electron shell altogether, and so it's now okay and happy and stable, but is considered a positively charged cation. And they form, in that whole opposites attract thing, a bond that attracts the two elements to each other. Covalent bonds share their valence electrons. So part of the time, the valence shell electrons will kind of hang out with one atom, and part of the time they'll kind of hang out with the other atom. And it's a sharing of these electrons. So it's not one giving them up to another. In the example here, you can see carbon and 4 hydrogens. And when we end up with our 4 single bonds between the carbon and each hydrogen, because carbon, with its only 4 electrons in its valence shell, wants 8, and so it has the ability to form 4 bonds. And here you can see the structural formula for methane, which is what CH4 is. We can also make double covalent bonds and triple covalent bonds. It's just a matter of how many electrons in the valence shell are being shared. There are 2 types of covalent bonds. There are nonpolar covalent bonds where the electrons are shared equally. These are electrically balanced, nonpolar molecules. They tend to have these kind of linear, symmetrical shapes like carbon dioxide here. And so since it's an equal sharing, the valence electrons spend and split their time evenly between kind of hanging out here with the oxygen and hanging out here with the carbon. It's a double bond because, again, we want the 8 electrons. Polar covalent bonds are an unequal sharing of electrons, and so it produces what we call dipoles, or polar molecules, of which the best example is water. The reason some atoms or some compounds and molecules form polar covalent bonds is that the atoms themselves kind of like the electrons to a different degree. So atoms that are really, really close to having their valence shell full, they have 6 or 7 valence shell electrons, for instance oxygen, then they're considered electronegative. They're so close to having a full shell that they attract electrons very strongly. Conversely, electropositive molecules, things with maybe 1 or 2 valence shell electrons, like sodium, because they're not as close to being full, they only attract electrons kind of very weakly. And so we get this kind of uneven distribution of the electrons. Let's look at what that looks like. Unlike the nonpolar covalent molecules, polar molecules tend to have this kind of V-shaped. They're not balanced anymore like carbon dioxide was. Oxygen is much more electronegative than the two hydrogens here. And so electrons spend much more of their time around the oxygen atom than they do around the two hydrogen atoms. It's not a full give and take like an ionic bond, but what we end up with is a slightly negative charge on the oxygen and a slightly positive charge on the hydrogen. This distribution here, this slight positivity and slight negativity, then allows polar molecules like water to form hydrogen bonds. Hydrogen bonds are not considered a true bond. They're really more of an attraction between an electropositive hydrogen and some other electronegative atom. And they form these very kind of temporary, ever-changing, what we call intramolecular bonds. And hydrogen bonds are responsible for many, many, many of the 3D shapes of our biomolecules that we'll talk about further on in the Chapter 2 series. So let's kind of look at what that looks like. I always like the videos. I like seeing stuff move. Ooh, didn't work. Let me go back. Previous. Play.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
So here you go. Here's what a hydrogen bond looks like. And as the video said, they are kind of temporary, but it takes a lot to break these. You can see the slightly positive hydrogen is attracted to the slightly negative oxygen, and it makes these intramolecular bonds that really help a lot of our biochemistry molecules stay together in their shapes. They are also responsible for all of the special properties of water that make it so cool and useful for us. Like, for instance, as the video said, it's very high surface tension. And because of that very high surface tension, that's why this little water strider here looks like he can walk on water. In fact, he can walk on water because of that very, very high surface tension. Before we end this one, let's go and talk about the stability of our different types of chemical bonds. As the video mentioned, the hydrogen bonds are the weakest of the chemical bonds because they're not considered a true bond. If we were to compare ionic bonds and covalent bonds are more stable than ionic bonds. Let's think of it this way. Say you're splitting a pizza with your buddy, and your buddy eats all the pizza and you get none of the pizza. that makes a pretty unstable situation, right? Because you wanted some of that pizza. So hydrogen bonds are the weakest. Ionic bonds are the next weakest. Remember, we have two types of covalent bonds. We have the nonpolar covalent bonds, where the electrons are shared equally, and we have the polar covalent bonds, where electrons are shared unequally. I think actually I can write here, can't I? So, oh, it won't let me. Darn, I was hoping I could write on the screen, but apparently it won't let me. Let's talk about those two types of covalent bonds, though. You've got equal sharing and non-equal sharing. Let's go back to our pizza example. If you are sharing a pizza with your buddy and your buddy gets 6 slices and you only get 4, then again, we still have a slightly unstable situation. And so polar covalent bonds, which share electrons unequally, are less stable. And really it is the non-polar covalent bonds that are the most stable type of chemical bond. That is because the electrons are shared equally. They spend their time evenly between the atoms in the molecule. So if we go back to our pizza example, you and your buddy are splitting a pizza. You each got 4 slices. It's a nice, happy situation. So again, from the top, as it were, hydrogen bonds are the least stable. They are not true bonds. They are an attractive force. Ionic bonds are more stable than hydrogen bonds, but less stable than covalent bonds because one atom takes away from another atom. Covalent bonds that are polar are more stable than ionic bonds because it's a sharing of electrons, but not equally, which makes polar covalent bonds less stable than nonpolar covalent bonds, which are the most stable of our chemical bonds because they represent an equal sharing of the electrons. Each atom, each person gets an equal slice of the pie. All right, that's it for part B.